This is the first video in AP Calculus in section 5.5, which is on the trapezoidal rule. Up to this point, we have found area under a curve using geometric properties if it forms like an exact geometric shape like a triangle or a rectangle or a portion of a circle. And then we've also estimated area under a curve using rectangles, left endpoint, right endpoint, midpoint rectangles. Today we're going to look at perhaps a more accurate, I don't know, it remains to be seen, but another way to estimate area under a curve, and that is through trapezoids instead of through rectangles. So the reason that trapezoids may be more useful in terms of estimation than rectangles is because when you have, like on this graph here, if you have a curved function graph, then those rectangles can't really mimic the curves very well. But if you have a trapezoid and you can here, for example, draw an angled side like that rather than a horizontal side, then you can get a little bit better approximation perhaps of the area within that section. But in order to be able to do that, that requires you knowing how to find the area of a trapezoid, because when we did rectangular approximation, we used area of a rectangle formula. So maybe you remember, maybe you don't. The area of a trapezoid is calculated using 1/2 times base 1 plus base 2 times the height. The only difference really is that you guys are used to, in your previous math classes, even back to elementary school, trapezoids usually look something like this or something like this. And the bases are usually these sides. They're the ones that are parallel to each other. Well, if you look at all the trapezoids drawn in this picture here, the parallel sides are the vertical lengths, and then the height is actually the change in x. So the height is going to be equal to your change in x, or right endpoint minus left endpoint, the width of that interval, just like it is with the rectangles that we've done so far. And then your bases, like for this trapezoid that I've outlined here, this would be base 1 and this would be base 2. The lengths of those correspond to the function values at those values of x, just like with the rectangles. Those heights of those rectangles, or those lengths of those rectangles, came from the y values at our x coordinates. Now, when you move to the second trapezoid, though, look what happens. This length that was base 2 in the first trapezoid, it's now base 1 in the next one, and here's base 2. Now this one gets a little funky because it switches between below the x-axis and above the x-axis, but this would be a base length in both this trapezoid and in this second interval here, even though it's a weird interval. This guy would be a base length in the interval to the left and the interval to the right of it. Same thing here. Same thing here. In fact, the only base lengths that only connect to one trapezoid are the very first one and the very last one. We'll call it B sub n. So as long as your trapezoids are equally spaced, like they are in this picture, then you can actually kind of streamline your rule rather than just doing 1/2 times b1 plus b2 times the height for every single trapezoid and adding them together. You can use this formula right here. As long as your height is consistent for all of your trapezoids. If they were not equally spaced, you couldn't use this streamlined approach. But look at how the streamlined approach is. You take whatever that height or that change of x is, divide it by 2, and then you add together all of the y values. Only the first and the last y value get used one time each, and all of the y values in between count twice because they're in two trapezoids. So that's your streamlined approach. But again, you can only do that if the subintervals are of equal length. If each of those trapezoids was a different measurement, you would have to use 1/2 times b1 plus b2 times h and do every trapezoid individually and add them all together. Now, another helpful way to find trapezoidal approximation is to actually take your estimate from LRAM and your estimate from RRAM, add them together and divide by 2. So the average of those actually equals the same approximation you would get using the trapezoidal rule formula. But to be honest, the only time that that's really helpful is maybe if you're doing a problem where you've already had to find LRAM and RRAM, then you can just average them together. But if you haven't already had to find them, there's really no point in doing those two and then averaging them just to find the trapezoidal rule. You might as well just stick to the other h over 2 times all those different y values approach. So let's look at a problem. So we want to use the trapezoidal rule with n equals 4 to approximate the value of this integral down here. And then we're going to compare that estimate with the value of math 9 in our calculator for the integral of the function. And then we'll talk about the concavity of the function and how that relates to the validity of the trapezoidal approximation. So I'm going to approach this the same way I've approached rectangular approximations in the past. I'm going to look at the width of my interval. So my interval goes from 1 to 2. So I'm actually going to start by drawing a number line that goes from 1 to 2. And then I need 4 subintervals. So just like that. So to figure out the width, or the change in x, you do end minus beginning divided by the number of subintervals, b minus a over n. So each subinterval is going to be 1/4 of a unit long. So if we start at an x value of 1 and add 1/4 to that, that would be 5/4. Add 1/4 to that, that's 6/4, or 3/2. Add 1/4 to that, and we get 7/4, and then add 1/4 to that, you get 8/4, which is 2. So I know that I've counted correctly. So my h is 1/4. So my trapezoidal approximation with 4 subintervals is going to be that h value divided by 2 times my function evaluated at each of those marks along my number line that I made. My function is what's inside the integral. So that would be 1 squared plus 5/4 squared, but it's an interior y value, so it's going to count twice. The next interior y value also counts twice, as does the next one. And then the last one only counts 1 time. You need to show that setup step. Whether it's something for me or it's an FRQ, you're going to get a point in there simply for showing that setup. So now let's calculate it. 1/4 divided by 2 is actually 1/8. And then this is 1 plus 5/4 squared is 25/16 times 2 is going to be 50/16. So I'm just going to leave it like that. I know it can reduce, but I'm going to leave it like that for right now. The next one is going to be 9/4 times 2 is 18/4. 7/4 squared is going to be 49/16 times 2 is 98/16. And then 2 squared is 4. So again, I'm working this as if I did not have a calculator. So common denominator would probably be good. So I've got 1/8 times 16/16 plus 50/16 plus, this would get multiplied by 4. So that's 72/16, 98/16, and 64/16. So that becomes 1/8 times 75/16. Let me double check that math. That can't be right. 66, 138, 236. It's 300/16. All right, so I went back and checked my math, and that reduces 75/4, excuse me. You get 300/16, which will reduce to that. So then you multiply that together, and your final answer would be 75/32, which is approximately 2.3438. So let's compare that estimate, 2.3438, to the actual area under the curve. So let's go to our calculators. And I'm going to hit Math 9. And then I'm going to put in that exact integral. You remember doing this previously, hopefully. And so the exact area under that curve from 1 to 2 is 2.333, 2.3 repeating. Our estimate was 2.344, which is an over estimate of the exact area. So if we go back and we read our question here, how could the concavity of the function help to determine if the trapezoidal approximation is an overestimate or an underestimate? So we're looking at y equals x squared. Here's maybe 1 to 2. So basically from here to here is what we're looking at for the area under that, okay? That graph's concave up. I ended up with an overestimate, so if they're kind of pointing us towards concavity, telling us something, then that would lead me to believe that when that portion of our graph is concave up, we're going to get an overestimate using the trapezoidal rule. So most likely, when our portion of our graph is concave down, the trapezoidal rule is going to give us an underestimate to the exact area under the curve. All right, so I want you to pause the video, and I want you to give example 2 a try for yourself. Try setting up the entire trapezoidal rule, use n equals 4 again, and then look at this compared to the exact area under the curve and see if it kind of confirms what we said about concavity. So pause the video and give it a try. All right, so as far as working without a calculator goes, you could do your setup step, which I have right here without a calculator, but then really at that point, you're stuck without a calculator. You can figure out cosine of 0 yourself from the unit circle, but 1/4, 1/2, 3/4, and even 1 are not exact angle measures on the unit circle. So you would have to rely on your calculator at that point. So I got for the trapezoidal approximation 0.837. But then when I calculate the exact integral from 0 to 1 for cosine of x, I get 0.841. So our trapezoidal estimate was an underestimate. Now, if we look at the cosine curve from 0 to 1, cosine starts off like this. So that's going to be a concave down graph, and I got an underestimate. So that does confirm what we kind of figured out in the last problem. Concave up is going to be an overestimate. Concave down is going to be an underestimate there. All right, so that's the end of the first video on trapezoidal rule. In the next video, we're going to take a look at applying trapezoidal rule to some type of conceptual problem.